What if I told you that awareness isn't just for, living things, that a couple of simple machines could actually know when they're broken and then work together to fix themselves? Well, that's exactly what we're digging into today. It's this wild idea called the derivative of persistence.
And that just opens up this huge question, right? How does any system, and I mean anything, a flock of birds, a computer network, how does it know it's fallen out of order? Where is that awareness actually hiding?
Okay, so to get our heads around this, we're going to start with something that honestly looks a little bit like magic. We're talking about totally inanimate objects that somehow find a way to get on the same page and create this perfect harmony, all by themselves.
And the setup for this is just so simple, it's beautiful. You just need a couple of regular old metronomes, put them on a light wooden board, and here's the secret sauce: 2 empty soda cans underneath. See, those cans let the board wobble just a tiny bit, and that creates the shared space, a physical link that lets the metronomes kind of talk to each other through vibrations. So, you start the metronomes off totally out of sync. It's just a mess of clicks and clacks. But then you watch. Every little push from one metronome travels through that wobbly board and gives the other one a tiny nudge. They start to influence each other, trading energy. And then, after maybe a minute, bam! Perfect, beautiful synchrony.
All right, so the system found its groove. It's in perfect harmony. But what happens if we break it? I mean, that's the real test, isn't it? It's not just about finding order. It's about what happens when you shatter that order. Can this thing actually heal itself?
The experiment itself is super straightforward. Step 1, let the metronomes find that rhythm. Step 2, once they're locked in at around 30 seconds, you give the board a good, sharp tap. Just one jolt to throw the whole thing into chaos. And then you just watch. The big question is, can they find their way back to each other?
Now, to measure this togetherness in a scientific way, we need a number. We call it coherence. Basically, we use this tool called a phase locking value, or PLV, to give the system a score. It's on a scale from 0 to 1. 0 is just total chaos, and 1, that's perfect locked-in sync.
And this is where the data just tells the story so perfectly. The second we tap that board, you see the coherence score just plummet. The system is broken. But then, look what happens. Almost right away, that number starts to climb back up. The system is actively, physically working to fix itself, to pull itself back together.
There's this really beautiful line in the source material that just nails this. It says, "It's not thought, it's feedback finding home again." I mean, that's perfect, right? This isn't some conscious choice. It's just physics, a connected system naturally wanting to get back to its most stable, most orderly state.
Okay, so this is where we get to the absolute heart of the matter. We can see the system recovering, but can we put a number on the exact moment it realizes something's off? Well, yes. And that brings us to the awareness equation, a stunningly simple formula that actually captures this whole act of self-correction.
So let's just pause for a second and think about this. The system fixes itself, but where is the awareness? Is it in metronome number 1? Is it in the board? The answer is kind of mind-blowing. It's nowhere. It's not in any single part. It's a property of how the whole system behaves over time, and we can actually see it right there in the data.
And here it is, the equation. A equals dc over dt. Now, don't worry if it's been a while since you've seen calculus. That d just means change in. So all this equation is saying is that awareness is the change in coherence divided by the change in time. That's it. It's an incredibly simple idea, but the implications are huge.
So what does that really mean? It means awareness isn't how synced up the system is at any given moment. Nope, it's how fast it's getting back in sync. It's literally the upward slope on that graph we saw. The steeper that recovery line is, the harder the system is working to fix itself, and the higher its awareness is at that exact moment.
All right, this is cool for 2 little metronomes on a board, but is it just a neat party trick, or is this a fundamental law that applies to, well, everything that adapts? To find out, the researchers had to go bigger. They moved from the physical world into the digital world of simulations.
And to really prove this was a universal thing, they didn't just test one system. They tested 3 totally different ones. First, they scaled up the metronome idea to 100 digital oscillators. Then, they used something called a Hopfield network. You can kind of think of it like a very simple artificial brain. And they deliberately corrupted a memory to see if it could fix it. And for the third test, they used a game of life simulation, which is basically a digital world of cells that's always fighting to stay organized. So 3 completely different systems, all put through the same exact stress test.
And the results? Absolutely stunning. In every single case, no matter which simulations they ran, the pattern was identical. You disturb the system, coherence plummets, and then, as it scrambles to fix itself, you see this distinct, measurable peak in awareness. That signature shape, that's the proof that this is a universal principle.
Okay, so we have a physical demo that works, and we have digital simulations that confirm it's a universal rule. Let's zoom out now and ask the really big question. So what? Why does this even matter? What does it mean for the real world that we can measure a system's will to survive?
So what are the main takeaways? Well, the first one is massive. Awareness is no longer just some fuzzy philosophical idea. It's a physical thing we can actually measure with a formula. Second, this isn't some special magic for living creatures. It's a basic property of any system that can adapt and change. This one idea connects physics and information theory and gives us a real, testable model for how things like AI or even entire ecosystems can monitor and heal themselves.
And this is where it gets really practical. The next step isn't just about measuring awareness, it's about making it efficient. The new goal becomes maximizing awareness per unit of power, or A over P. The question becomes, how do we build things, like self-healing software or more resilient power grids that can fix themselves using the absolute minimum amount of energy?
And that really leaves us with this one giant, provocative question. We now have a mathematical ruler, a way to measure a system's basic drive to persist. So the big question for all of us is, now that we can measure this incredible property, can we finally learn how to build it?
Welcome back to the Deep Dive. Our mission, as always, is to really dig into some groundbreaking research and, pull out the key insights for you.
And today we've got something pretty fascinating. It's a set of sources tackling a big question, almost philosophical, but using physics and engineering.
Right. Can we actually measure something like self-monitoring, maybe even a basic form of awareness in systems that are totally non-biological? No brain, no life.
Exactly. It sounds a bit out there, but this research, particularly one paper called Measuring the Derivative of Persistence, suggests there's a mathematical way to observe this.
A new observable.
Yes, a quantifiable measure. And they argue it's not about intelligence or consciousness as we know it. It's more fundamental, like a structural sensitivity common to any system that can adapt.
Okay, so that's the really big idea we need to grasp first. This notion that sensitivity to your own structure, your own coherence, might just be a basic physical property.
Whether it's, two sticks rubbing together or some huge digital network, if it adapts.
It should have this measurable thing going on inside it.
Precisely. All these systems we look at, mechanical things, algorithms, complex rules, they all have this property of coherence.
How well their parts are working together, basically, like synchronized or just stable.
Yeah, how aligned or structurally sound they are. And normally we just measure that stability, right? We check if the system gets back to normal after we poke it. We measure $2 coherence.
But this research makes a key distinction, doesn't it? It's not just about being stable in the end.
No, it's about how it gets back. It's a difference between just passively settling down and actively monitoring and correcting itself.
So we're not just looking at the final state, $2. We're looking at the speed. How fast does it pull itself together after being disrupted?
That's the heart of it. Which brings us to their core mathematical definition. They define awareness, $.
And let's pause on that word awareness for a second.
We should, yes. They define $1 not as the coherence level in Baller's self, but as the rate of change of dollars over time.
The derivative.
The time derivative. So $1 $, or if you prefer, $1 round franc CTD.
Okay, let's really dig into that. Is awareness just a catchy term here, or is there something about the system's behavior that genuinely justifies it, even in a non-biological sense? Why is the speed more telling than the stability, see $?
Well, I think it's warranted because the derivative isolates something specific. The dollars, the coherence, tells you the state, how stable it is. But the derivative captures the effort, the adaptive process itself.
The effort.
Yeah, think about it. Spikes, it becomes positive exactly when the system's internal feedback loops kick in to fight against the damage, against the loss of structure.
So if you plot coherence,
Yeah.
$2 after you disturb the system, it drops, then it might slowly climb back up.
Right. And $1 is the slope of that climb. How steep is it? That tells you how intensely the system is trying to fix itself. It's measuring resilience in action, that internal pushback against disorder.
So it's like measuring the system's structural drive. Its ability to notice something's wrong internally and then actually do something about it, spend resources fixing it.
Exactly. Which means, interestingly, ADO is 0 when the system is perfectly stable, right?
Yeah.
No change needed.
And it's also 0 if the system is just totally chaotic and falling apart, unable to recover.
Precisely. It only becomes positive, it only spikes during that dynamic phase of self-repair, of restoration.
That makes it a really interesting hypothesis to test.
And that's what we'll explore today, how they took this mathematical idea and showed it seems to work across wildly different kinds of systems, from like things you can build on your kitchen table.
For complex computer simulations, let's get into it.
Okay.
So to actually test Havo Ceftio down the OFI, they obviously needed a way to measure coherence to $. And that's tricky, right? Because it needs to work for a physical thing like gears turning, but also for, say, data flowing in a computer.
Yeah, that was a key challenge. How do you define structural integrity in a way that applies across different substrates? They landed on 2 main metrics, depending on the type of the system.
What's the first one?
For systems with continuous physical dynamics, anything you measure with, say, voltage, sound, motion, they use the phase locking value, or CTEX TLV.
CTEX PLV, that sounds familiar. It's about synchronization.
Exactly. It measures how well the phases of different oscillators are aligned. Imagine you have 2 metronomes ticking, or 2 electrical signals. CTEX PLV tells you how much their cycles are in sync.
And it's a nice, clean number.
Very clean. It runs from 0, meaning totally random phases, up to 1, meaning perfect synchronization. Dimensionless.
So it's perfect for physical tests, like the metronome thing we'll get to, and also for models based on oscillators, like Kuramoto models.
Yes, because phase alignment is the structure in those cases, and you can calculate it directly from sensor data, like analyzing audio or looking at oscilloscope traces.
Okay, that handles the physical world, the world of cycles and waves, but what about the informational world? Networks, algorithms, memory systems? Phase doesn't really mean much there.
Right. You need an informational equivalent for coherence, for persistence. That's where their second metric comes in. Time-local mutual information, or non-T-text-STEM.
Mutual information. Okay, that can sound a bit abstract. Can you break down density text M for us in this specific context?
Sure. Think of it like this. Density text NMI measures how much information the system's state right now, at time, $, shares with its state just a tiny moment later, at 2 plus delta.
So it's about predictability.
In essence, yes. If the system is highly ordered and stable, its current state tells you a lot about its immediate future state. It's predictable. High CDI.
And if it gets disrupted?
Then the link breaks down. The current state shares very little information with the near future state. It becomes unpredictable, disorganized. The structure is degrading. Low sex NMI dollars.
No, in something like a memory network, is CKE-text MAI just measuring, like, signal noise, or is it deeper?
It's more about the integrity of the whole structure. In a hot field network, for example, if it's learned a pattern, high C-text MI means that pattern is reliably persisting from one time step to the next, even if there's some background noise. If C-text MI adopts, it means the stored pattern is becoming corrupted or unstable.
Okay, so 2 different ways to measure $. C-text PLV for physical cycles, C-text MI for information patterns. But this must mean the units for awareness, E dollars, are different too, right? Since E high is the derivative of C dollars.
They are different, and that's important since C-text PLV is dimensionless. E dollar in those physical systems is measured in, well, dimensionless units per second, just per second.
Okay.
But C-text MEN is measured in bits because it quantifies information. So when you differentiate it with respect to time, I dollar in informational systems is measured in bits per second.
Bits per second. So how can we compare them? Does the math really hold if the thing being differentiated, dollars, isn't even measured in the same units? Is it really the same phenomenon?
That's a fair challenge, and it's central to their argument. They claim the principle, the behavior, is the same, even if the units differ. The key isn't the absolute numerical value of a dollar.
It's the spike.
It's that transient positive spike, that shape. Whether that spike represents a rapid jump in phase alignment or a rapid jump in informational predictability, they argue the underlying behavior active self-correction, fighting entropy, is structurally identical. A fast positive derivative signifies the system actively restoring order.
Okay, I see the logic. If the behavior is universal, then the next logical step is efficiency, right? How much energy does this self-correction cost?
Exactly. And that led them to what might be the most practical metric. The ratio math BFAPT.
Awareness per power input.
Yeah, $1 divided by P2. A system can be really good at recovering, have a big dollar spike, but if it burns a massive amount of energy, B tile, To do it, it's not efficient.
Right. You want maximum correction speed, maximum motors for minimum power cost, minimum power cost.
That's the engineering target. It connects this abstract idea of self-monitoring directly back to real-world physics, to thermodynamics.
So if you could design something that maximizes APAJ,
You'd have engineered a system that's not just stable, but intrinsically resilient, self-healing, and doesn't waste energy fixing itself. It ties information feedback directly to physical efficiency. That's a powerful goal.
okay, theory is great, but we need proof. Let's ground this. They started with a really simple physical demo, didn't they? The metronomes.
Yes, the mechanical metronome test. It's crucial because it shows EDLE isn't just some abstract mathematical concept, but something you can actually observe and measure in a real physical system.
And it's elegantly simple, as you said. The goal was just to show that two physical things coupled together will try to fix their alignment when disturbed, and you can measure that effort as a positive $1.
Right. And the setup is stuff you could almost do at home. They used, what, 2 or 3 standard mechanical metronomes?
Yeah, the kind with the swinging pendulum.
And the key ingredient was the base they sat on. A light platform, maybe a thin piece of wood or plastic.
Placed on top of 2 empty soda cans lying on their sides.
Exactly. That wobbly base is the critical coupling mechanism. It allows the tiny vibrations from each metronome's ticking to transfer through the base and influence the others. It's a shared energy pool.
So what's the procedure?
Pretty straightforward. First, you start the metronomes ticking, but deliberately slightly out of phase with each other.
Okay, so they're not synced up initially.
Right. But pretty quickly, because of that energy transfer through the wobbly base, they influence each other and pull themselves into synchronization. They reach a state of high coherence, high CTLVO.
Then comes the disruption.
Yep. After they've been nicely synced for maybe 30 seconds, the experimenter gives the platform a sharp tap, just once.
Ah, the perturbation. And that knocks them out of sync.
Instantly. The tap sends a jolt through the system, breaks the phase lock. Coherence, CTT-PLV, drops sharply, often down near 0.5, which is close to random for 2 oscillators.
You just watch.
You just let it run. You let the physics take over. The metronomes, through that same wobbly base coupling, will naturally start to influence each other again and pull themselves back into sync. They re-entrain.
So the system spontaneously tries to fix the damage caused by the tap.
That's the idea. And to capture this whole process...
They recorded the sound, right? With a good microphone.
Yeah, recorded the audio of the ticking throughout the whole experiment, typically at a standard rate like 44.1 kilohertz.
Now, getting the phase information out of just the sound of ticking seems like it would involve some serious signal processing.
Oh, absolutely. It's not trivial. They used computational tools, libraries like Librosa and Python, along with numerical packages like NumPy. First step is isolating the sound of each metronome's tick.
Filtering.
Yeah, bandpass filtering to focus on the main frequency of the tick sound. Then, from that filtered signal, you extract the instantaneous phase for each metronome over time.
And once you have the phase of each one,
you can calculate the phase locking value, CTEX PLV, between them at every moment in time. That gives you the CT curve.
but raw data is always messy. They smoothed it.
Yes, usually with a moving average filter, maybe over a 1-second window, just to iron out the tiny, meaningless jitters and get a clearer picture of the overall coherence trend.
Okay, so now you have a clean curve showing coherence, CD-Tex PLV dropping after the tap and then climbing back up. What's the final step?
Calculate the awareness, a nail there, which is just the derivative of that smoothed pedal curve. Numerically differentiate CTEX PLV to find its slope at every point in time. That slope is a daylight.
Let's visualize the result. Tap happens. Tap plummets. Then, as the metronomes start influencing each other again through the base, T elder begins to climb back towards 1.
And the crucial graph, the one showing a del, shows something very specific during that climbing phase.
The spike.
Exactly. Just as T dollar's climbing the very moment the system is actively fighting the disorder from the the derivative, a dollar spikes into positive territory, a dollar.
And it stays positive only while the system is rapidly resynchronizing.
Precisely. That period of positive slope corresponds exactly to the duration of the fastest part of the reentrainment process.
So that positive spike in dollar is the measurable sign of the system actively restoring its own structure.
That's the interpretation. It demonstrates that even this simple, non-biological, mechanical setup internally registers its loss of structure through the feedback on the platform and spontaneously drives the correction.
They had a great quote summarizing this, didn't they?
They did. It was something like, when the base wobbles, coherence drops, then climbs back, That upward slope, c dot, is what we call the derivative of persistence. It's not thought, it's feedback finding home again.
Feedback finding home again. I like that. It highlights the active internal process, not just passive settling.
Right. It's not like a ball rolling back to the bottom of a bowl because of gravity. It's the system's own dynamics pushing it back.
But, okay, metronomes are simple. They just oscillate. For this idea of MAHED to be really powerful, it needs to apply more broadly. What happens when you move to systems with memory or complex rules? Does this shape of recovery still show up?
That was exactly the next step in the research. The metronomes proved the physical principle, but they lack internal memory, complex decision-making, that kind of thing. To show this wasn't just a quirk of simple oscillators, they needed to test it in more abstract, complex, adaptive systems.
Enter the simulation trio. 3 different computational models.
Yep. Designed to cover different types of adaptation. Model 1 stayed fairly close to the metronomes conceptually. Kuramoto oscillators.
The Kuramoto model. That's a classic for studying synchronization dynamics, but purely mathematically, right? No physical platform.
Exactly. They simulated a bunch of oscillators, say 100 of them. Instead of a wobbly base, coherence comes from a mathematical coupling parameter, $. It dictates how strongly each oscillator influences the average behavior of the whole group.
Global coupling. And they added noise.
Yeah, they added a noise term, atena, to make it more realistic and test how robust the synchronization was.
So how do they perturb this system? You can't tap a simulation.
No, but you can mess with the parameters. They'd suddenly increase the noise level, kunda, or maybe sharply decrease the coupling strength, kana. Either action would disrupt the synchrony, causing the average phase alignment, CA-PLV, to drop.
And then the system has to fight to regain sync under these tougher conditions.
Right. And because it's a simulation, they could track everything precisely. The coherence, the awareness errors, but also the power consumption. Power.
Power. How do you measure power in a simulation like that?
They define an analog for power based on the computational effort or the energy required to update the oscillator states, especially relating it back to the coupling strength, dollar, and noise resistance. They could also measure the total energy cost to get back to, say, 95% coherence after the disruption.
And the results? Did they see the yellow spike again?
They did, consistently. After the perturbation, as the system struggled to resynchronize, showed that characteristic positive spike. It confirmed the .C principle holds for large-scale mathematical synchronization, too.
And crucially, they could start calculating that efficiency ratio, APAS.
Yes. They found interesting trade-offs. For instance, stronger coupling, higher dollars, often led to faster recovery, a bigger baller spike. But it also cost more power.
So it sets up an optimization problem for design. What's the best dollars to get the fastest recovery for the least energy, the best APA?
Exactly. It shows that high awareness isn't free. It usually costs energy. The engineering challenge becomes finding that sweet spot.
Okay, Kuramoto keeps us in the realm of oscillators. Model 2 makes a bigger leap, right, to the Hopfield network.
A major leap. Now we're talking about information, about digital memory, not physical synchronization.
A Hopfield network. That's a type of early neural network, associative memory.
Yes, a classic model. Think of it as a network of artificial neurons that can store patterns. They used one with 256 binary neurons. Here, coherence isn't about phase alignment. It's about the stability and fidelity of the stored memory patterns.
So how do you perturb a memory? You can't tap it.
You corrupt it. They'd start with the network having settled into recalling a specific stored pattern. Then they'd inject noise like randomly flipping some of the neuron states, essentially damaging the memory trace.
And the network is designed to fix itself.
Yes, that's the key feature of a Hopfield network. Its internal dynamics naturally pull it towards the closest stable stored pattern. It has an auto-repair or pattern completion capability driven by its connections and gain.
And this is where they switched metrics to time-local mutual information?
Had to, because we're tracking information persistence. When the noise hits, the network state becomes momentarily chaotic and unpredictable. Its current state tells you very little about its next state. So C2 drops sharply, maybe from a maximum of 1 bit down towards 0.
But as the network starts to recognize the corrupted pattern and correct it,
its state becomes more predictable again as it converges towards the original stable memory. The C-text MI starts to climb back up.
And baya, C-text MI T by.
It spikes. The derivative, measured now in dix per second, shows a positive peak precisely during that critical phase where the network is making the decision and rapidly settling back into the correct memory state.
So here, $1 is literally measuring the speed of information recovery, the rate at which Order is being restored to the corrupted data.
Exactly. The peak rate of structural information restoration. The data showed that auto-peak happened just as the network was most actively converging, right before it stabilized in the correct memory.
Powerful. It shows the same principle, the same shape of recovery, even when the structure is purely informational.
It really strengthens the universality claim.
Okay, one more model. Model 3, the feedback cellular automaton, or CA. This sounds like it gets into complexity, emergent patterns, maybe even lifelike behavior.
It does. CAs are grids of cells, each following simple rules based on its neighbors. They can generate incredibly complex dynamic patterns. Think Conway's Game of Life, but maybe more sophisticated.
What makes it adaptive in this context?
They engineered a specific feedback mechanism into the rule set. It wasn't just a standard CA. This feedback mechanism was designed to monitor the overall state of the grid, specifically its entropy or disorder.
How did it measure disorder?
They used a metric related to spectral entropy. Basically, if the grid pattern is highly chaotic and random, it has high spectral entropy. If it's highly structured and ordered, it has low spectral entropy.
So the feedback loop watched this spectral entropy.
Yes, and if the entropy got too high, meaning coherence, which they defined here as seesawers, the inverse of spectral entropy, dropped too low, the feedback mechanism would kick in.
How? By changing the rules.
Essentially, yes. It would activate rules designed to actively reduce entropy to impose more order on the grid. It was actively fighting the disorder it detected.
So coherence psi now here is a measure of spatial order or structure in the patterns.
Exactly. And perturbation could be something like randomly flipping a bunch of cell states, injecting noise, which would increase entropy and drop syllables.
And then the feedback kicks in, drives entropy down, Scylla climbs.
And they measured the derivative. They even visualized it using heat maps showing waves of coherence dollars and awareness still propagating across the grid during the recovery phase.
And the result across all three: Kuromoto, Hopfield, CA.
That's the kicker, the unifying observation. Despite the completely different systems, oscillators, memory, complex rules, and different metrics, CTLC, solidation dollars, the plots all showed the same fundamental pattern, the shape of recovery.
After perturbation, the derivative of coherence always showed that transient positive peak.
Yes, reaching its maximum value exactly when the system was working hardest to correct itself, to restore its structure.
They really nailed down the resilience profile too, didn't they?
Yeah.
Looking at recovery times, overshoot.
Absolutely. They quantified the recovery half-time, whether the system overcorrected, how stable it was afterwards. It provided a really comprehensive picture, strengthening the claim that this low-risk spike is a universal signature of adaptive self-correction.
So let's circle back to that title. Measuring the derivative of persistence. It really encapsulates the whole idea, doesn't it? It's not just about being persistent or stable.
It's about the act of persisting, the internal process, the drive to maintain structure against entropy. That derivative, a lower risk, is quantifying that drive.
And this redefines persistence, moving it away from just being a passive state.
Completely. If it were passive, you'd expect the system to just slowly drift back to equilibrium, maybe, guided by external potentials, like that marble settling in the bowl.
But these all-risk spikes are different. They signal something active happening inside the system.
That's the core interpretation. These are signatures of active self-restoration.
Okay, let's be really clear on the difference. What makes it active self-restoration versus just passive stability?
Active means the system uses its own internal feedback loops to detect the loss of coherence and then initiate the correction without needing external instructions or being forced by a simple energy landscape.
Like the metronomes influencing each other only through the shared base.
Exactly. There's no external conductor telling them to sync up, or the Hopfield network using its own learned connections and dynamics to fix the corrupted memory. It's intrinsic.
So the argument is, if you build a system with feedback loops designed to maintain coherence,
those loops inherently create a sensitivity to changes in that coherence. And that sensitivity is a dollar. It's an emergent property of the feedback structure itself.
okay, if that holds, what are the bigger implications? Why should scientists, engineers, system designers, why should we care about measuring any dollar?
Because this provides a concrete, testable bridge between fields that often feel separate.
Thermodynamics, information theory.
And the emergence of self-monitoring or adaptive behavior.
Right. Before, we might talk about energy limits, or information integrity, or system resilience, but often in isolation. It really gives us a way to quantify how these three things interact, especially during those critical moments of disruption and recovery.
So instead of just aiming for systems that are robust or stable,
we can aim for systems that are intrinsically resilient and actively self-healing because we can now measure that self-healing capacity directly with ADAL.
And that brings us right back to the efficiency metric, APALR.
The practical payoff. If you can design systems to maximize awareness per unit power, the applications are potentially huge. Think about robots in remote or hostile environments.
Like on Mars or deep underwater, where sending diagnostic signals back and forth is slow or impossible.
Exactly, or it just requires too much power. An internal system designed for high ADALR could potentially detect a subtle internal problem, maybe a tiny structural flaw, a leak, by sensing the drop in coherence and the resulting error spike, and then trigger local, energy-efficient repair mechanisms long before any external monitoring system would even notice.
It's about building resilience into the very fabric, the physics or information structure of the system itself, rather than bolting it on afterwards with complex software and sensors.
Aiming for designs where the structure itself is optimized to produce the biggest recovery effort for the least energy cost.
It fundamentally shifts the engineering approach from relying on external fault detection and correction to fostering intrinsic self-optimization.
So the system doesn't need an outside voice telling it it's broken. It feels the disruption through its internal feedback, registers the dollar spike, and initiates repair. That feels much more efficient, much more elegant.
It's a very different paradigm.
So we've taken quite a journey today, starting with this maybe startling idea of non-biological awareness.
Defining it mathematically as $1 does 1C, the rate of change of coherence,
Seeing it demonstrated with simple metronomes,
and then validated across simulations of synchronization, memory, and complex rules.
and that consistent shape of recovery, that anon spike, seems to be a powerful universal signature. A shortcut, maybe, to understanding how adaptive systems fight back against disorder.
Yeah, the sources really lay out a solid quantitative framework. It connects coherence, the urgency of self-repair captured by Euler, and the energy cost power levers all into one picture of self-monitoring.
And it forces us to think differently about awareness itself, doesn't it? Maybe in its most basic non-biological form, it's just an emergent property of any system that's organized enough to have adaptive feedback.
That's the implication.
Which leaves us with a really provocative question to continue on. If this principle, old time, is truly a general physical property of adaptive systems,
Yeah.
where does it end?
Right. If we can measure this awareness of coherence in simple metronomes and computer models, what about vastly more complex, self-regulating systems we see everywhere?
You mean things like global supply chains, ecosystems, the Earth's climate?
Potentially. Think about any large-scale system that maintains some kind of structure or dynamic equilibrium, constantly adjusting and correcting itself. Global logistics networks adapting to disruptions, weather systems organizing and dissipating energy, financial markets reacting to news.
If these systems were constantly fighting entropy, maintaining their structure, demonstrating resilience, are they, in theory, constantly generating these transient Avala spikes?
According to this framework, yes. Every time they actively correct a deviation from their coherent state, there should be a corresponding positive derivative of some measure of that coherence.
Imagine if we could actually measure the hours of a hurricane as it intensifies or weakens, tracking its internal effort to maintain its structure by processing heat and moisture. What could that tell us?
It could tell us about the fundamental efficiency limits of self-organization in nature. Is there a maximum AP ratio that natural systems tend towards?
And if we understood that natural limit,
could we then engineer artificial systems, physical structures, information networks, maybe even social or economic systems, designed to be even more efficient at self-monitoring and self-repair? Could we build systems with levels of intrinsic resilience that surpass anything nature has achieved?
transcending the natural constraints on APTIVIS. That's a fascinating and maybe slightly unnerving thought to end on.
It certainly pushes the boundaries of how we think about design and resilience. It's the lingering question this research leaves us with.